Here we're going to do a type of classic calculus problem which is skipped in almost every calculus course that I've ever heard about. And that is finding the solid of revolution where you're not revolving about a vertical axis or a horizontal axis, but we will be revolving about a slanted axis. We're just going to work out an example. I think you can probably work out a general formula for this, but I think there's a lot to be gained just by looking at a nice example. So in particular, we want to find the volume of the region formed by rotating the region bound by y equals x and y equals x squared about the line y equals x. Well, seeing this setup in all of these words is not super helpful. So let's maybe get a nice picture on the board in place of these words. That's better. So notice we've got our xy coordinate plane. We have our line y equals x, and then we have our parabola y equals x squared. So notice this region between x equals 0 and x equals 1 is bound by these two curves. Now, if these curves were a little bit more complicated, we might need to do some work to figure out that these are intersecting at 0, 0 and 1, 1, but it's pretty clear when we've got these two fairly simple curves. Okay. And now from here, we want to rotate this two-dimensional region about this line y equals x. I think there's a couple of strategies to do this. And in fact, I didn't really look up the standard method. I just kind of went with my gut and came up with what I thought would be the maybe most obvious method. And that's what we'll do here. Okay, so how can we get started? Well, first off, I want to split this interval from 0 to 1 into n equal subintervals. And we'll do that because the approach that will be taken will be to write our goal volume via an approximation as a Riemann sum, and then take a limit of that approximation in order to get the exact volume. So just to reiterate what's going on here, I'm going to set x0 equal to 0, and then x1 will be bigger than that, x2 will be bigger than that, all the way up to xn minus 1 and xn, which will be equal to 1. So in other words, I have partitioned the interval from 0 to 1 into these n equal subintervals. So let's encode that they are equal. So notice that delta x will be defined to be xi plus 1 minus xi. But since these are equal, that needs to be 1 over n. And that's because we're partitioning a interval of unit length into n pieces. Now, next up, I'll go to an arbitrary subinterval between 0 and 1 and look at the situation that's happening on that arbitrary subinterval. So I'll pick the subinterval with left-hand endpoint xi minus 1 and right-hand endpoint xi. Okay, so now bringing these 2 points up to our line, we see that those intersect our line at the coordinate xi minus 1, xi minus 1, and then the coordinate xi, xi. But now in order to approximate this rotation about the line y equals x, we can't use this rectangle or this approximation that is being built out of just these vertical line segments. Instead, we need line segments that intersect this line y equals x at a right angle. Okay, so let's drop a perpendicular from xi, xi until it hits the parabola. So this is going to hit the parabola at some point, and I'm just going to say that we need this point. That will be something that we're going for. And then what we'll do with this point is complete a rectangle. So we'll complete a rectangle like this, and then visualize that rectangle being rotated about the line y equals x, and that will create a disk. We can add up all such disks and take a limit, and that'll give us our volume. Okay, so let's transport this picture of this rectangle over there, and then we can get started with the calculation. Okay, we've got our rectangle translated over from this picture. Notice I have my line y equals x right here. And then I have these two coordinates xi minus 1 comma xi minus 1 and xi comma xi. So those are on the line y equals x. Then we're dropping a perpendicular from that line and it needs to hit the parabola. And I've highlighted this point here that we need to calculate the coordinates of. Well, in order to calculate those coordinates, I think we could make a couple of observations. So this line segment right here that's being dropped down is perpendicular to the line y equals x. But we know something about lines that are perpendicular and their slopes. Their slopes are negative reciprocals. So the slope of y equals x is 1. That means the slope of this line must be equal to -1. So that's a good piece of information. Also, since this point right here is on the parabola, we know the form that this point takes. Notice it must take the form t comma t squared. Well, x coordinate t, y coordinate t squared because it's on the parabola y equals x squared. So now we can just calculate the slope of the line between these 2 points right here, xi and t squared, set that slope equal to -1 and solve for t. So let's do that. So we have, on one hand, the slope can be calculated as change of y over change of x. So that's going to be t squared minus xi over t minus xi. And on the other hand, we know that the slope has to be -1. So that's equal to -1. But now cross multiplying, we very quickly get x squared minus t squared minus xi equals xi minus t. And then moving some things around, we see that we have a quadratic equation where t is the variable. So we have t squared plus t minus 2 times xi is equal to 0, keeping in mind that xi is a constant. We can use the quadratic formula here. That will give us t equals, so negative b, but b is 1 in this case, so it's -1 plus minus, but we'll just need the positive root. That's because the negative root would be the intersection that's happening over here. The square root of, let's see, it's going to be b squared minus 4ac, but that's going to leave us with 8xi plus 1. And then this is all over 2. Okay, so that's the value of t, but that means we can also calculate the value of t squared pretty easily just by squaring this. So let's see, that's going to give us 1/4 from squaring the half, and then we'll have -1 squared, which is 1, plus this square root squared, which is 8xi plus 1. And then we'll have twice the cross term. So that'll be -2 times the square root of 8xi plus 1. So that's our t squared term. Okay, so now that we've got t and t squared, let's maybe go ahead and take those coordinates and bring them up here. Okay, we just got done calculating this coordinate here. So this thing that I said need point, well, we no longer need it. It has this like crazy form here in terms of xi, which is the point, well, it looks like it's above it here, but it really follows on the line y equals x at a 90-degree angle. So now let's see what we're gonna do next. The next thing that we'll do is rotate around the line y equals x. That's going to turn this rectangle into a disk. Okay, so we rotate this around the line y equals x. That gives us this disk. Now, in order to find the volume of that disk, which will be of the utmost importance, since we're going to eventually add all those volumes together to find the volume of this rotated region, we need the radius and the thickness. Notice the thickness, which maybe I'll call W at the moment for width, will be the distance between these 2 points. Now let's mock up the width right here. Then, like I said, we also need the radius, so that will go from the axis up to this curve. So I'll call that R. Notice the radius R will be the height of this rectangle. Okay, so now let's get to calculating those. Since these endpoints are given by coordinates, we can use the distance formula to calculate each of those distances. So let's notice that W will be the distance between these 2 points that are on the line y equals x. So we've got xi minus 1, xi minus 1, comma, xi, comma, xi. So just using the standard distance formula, we know that that is the square root of xi minus 1 squared plus another copy of that. And that's because we're on the line y equals x, so the x and the y coordinates are the same. This is like the change in the x coordinates, and that's like the change in the y coordinates. But let's recall that xi minus 1 is defined to be delta x. This is shifted a little bit, but we always get the same value. So this gives us the square root of delta x squared plus delta x squared, which is 2 times delta x. So in other words, we have the square root of 2 times delta x. So let's maybe include that in here right here. This width is the square root of 2 times delta x. And if you're familiar with the construction of standard solids of revolution, you know that something like delta x should have come out of this. Okay, now let's calculate this radius. And this is a bit gnarlier to calculate, but all in all, it's kind of the same process. We want to find the distance between this point and this point. Just to save myself some writing, I'm going to name these points things. So let's name this point up here P, then we'll name this point right here Q. And so R will be given by the distance from P to Q. And again, we will use the distance formula. So that'll be the square root of the difference of the x coordinates. So maybe I'll do the top one minus the bottom one. I'll write this xi as 2xi over 2 just to make it work with this a little bit better. And that's going to leave us with 1/2 times the quantity 2xi plus 1 minus the square root of 8xi plus 1. And then all of that must be squared because it's the difference in the x coordinates squared. So just to reiterate, I did this x coordinate xi minus this x coordinate. Okay, but then something a little bit magical happens. And that is if you do this xi coordinate minus this xi coordinate, you don't get exactly the same thing, but you get a negative of the same thing. But since we're squaring this whole thing, well, the negative doesn't really matter. So that means we're going to get another copy of the same thing. That's going to give us 1/2, then 2xi plus 1 minus the square root of 8xi plus 1. And then all of that is squared. Okay, so now via a similar process to this right here, we can add these two things together. That'll give us a square root of 2 times this thing right here where the square and the square root cancel each other. Okay, so that's going to give us, well, the square root of 2 over 2, that's 1 over the square root of 2. And then we'll have 2xi plus 1 minus the square root of 8xi plus 1. Great. So that's our radius of our disk. Okay, so let's maybe bring some of this information to the top, and then we're ready to finish the calculation off. So on the last board, we found the radius and the width of the disk formed by rotating the rectangle defined on the xi minus 1 xi subinterval around the line y equals x. They had some sort of a complicated structure, but they're workable. So now we know that the volume of our entire object will be equal to the limit as the number of subintervals goes to infinity, so here we've got n subintervals, but if we let n go to infinity, we know we're going to get an exact solution instead of an approximate solution. And then we'll sum from I equals 1 to n of the volume of each of these disks. But let's recall that the volume of a disk, maybe we'll call it VI for the ith disk, will be equal to pi times this radius squared times the width. So that's a standard formula for the volume of a disk. So let's maybe take that pi and put it out here. And then we can take this radius squared. Notice that's going to give us 1/2, and then 2xi plus 1 minus the square root of 8xi plus 1, everything squared. Like I said, that's our radius squared. And then we'll have our width, which is the square root of 2 times delta x. Okay, so now let's get to simplifying that. That's going to be this limit as n goes to infinity of, let's take everything out that we can. We have pi times the square root of 2 times delta x. None of those depend on I. And then we'll have the sum as I goes from 1 up to n of this thing squared. Oh, I can also take this 2 out. So that's going to be root 2 over 2. So let's see what we get when we square this. So we will have 2xi plus 1 squared. That'll give us 4xi squared plus 4xi plus 1. Then we'll have this object squared. That'll give us plus 8xi plus 1. And then we'll have the cross term. But that cross term will be minus 2 times 2xi plus 1 times the square root of 8xi plus 1. Okay, now we can get to combining like terms. So let's see, this term and this term are similar, and then this term and this term are similar. So we can put those together. That's going to leave us with this limit as n goes to infinity. I'm going to write this as pi over the square root of 2 times delta x times our sum as I goes from 1 to n of 4xi squared plus 12xi plus 2, and then we'll have minus 4xi times the square root of 8xi plus 1 minus 2 times the square root of 8xi plus 1. But now this limit of this sum can be transformed into an integral. That will leave us with pi over the square root of 2, and then we'll have the integral from 0 to 1, because we're partitioning that interval, of 4x squared plus 12x plus 2 minus 4x times the square root of 8x plus 1, and then minus 2 times the square root of 8x plus 1 dx. So we have that integral in order to finish off our calculation. On the last board, we got to the following integral, which is giving us our goal volume. Now let's maybe calculate some of the steps of this integral, but we might just jump to the solution. So I'll first break this apart into two integrals, because we've got this polynomial part, which should be fairly easy to calculate. And then we have the rest of this part, which is maybe a little bit trickier to calculate. So we'll have pi over the square root of 2, the integral from 0 to 1 of 4x squared plus 12x plus 2 dx. And then we'll have the rest. Notice I can factor out a minus 2 from that. So I'm going to have minus 2, the integral from 0 to 1 of, let's see, I'll have left 2x plus 1 times the square root of 8x plus 1 dx. And I know I had those together before and I separated them out, but I'm going to put them back together. So now let's calculate this bit really quickly. So notice the antiderivative here will be equal to, let's see, 4 over 3x cubed plus 6x squared plus 2x. We need to evaluate that from 0 to 1. So I'll let you guys do the arithmetic. That shouldn't be too bad. And then what do we need to do on this last bit? I think there's probably a couple of strategies here. I would maybe use a u substitution. So let's take u and set it equal to 8x plus 1. That means du is equal to 8 dx, which tells us that dx is equal to 1/8 du. So that means when we replace dx, we need to replace it with 1/8 du, like that. Next, we can solve this thing for x, and that's going to give us, let's see, x equals u minus 1/8. That'll be helpful for plugging in right here. Okay, so let's see what that gives us. We've got 1/8 du. That will combine with this minus 2 to give us minus 1/4. And then we'll have the integral of, well, let's plug this in for x. That will give us u minus 1/4 plus 1 times the square root of u du. Then let's see our bounds of integration. Those will be 0 plugged in for x, which gives us 1 for u and then 9 for u. Now you can finish this thing off with the power rule after distributing the square root of u through. So I'll leave that to you, and maybe I'll just jump to the solution if you want to check your work at the end. So when all is said and done, the volume will be equal to pi over 30 times the square root of 2. And that's a good place to stop.